Okay, so having provided some of the high-level motivation and big picture behind what MapReduce is and where it is being used, let's now go into a bit more detail about what MapReduce is and give you a little bit of background on the programming model and how MapReduce typically is executed before I come to some of the research that we are carrying on. So at a high level, this is what a MapReduce computation looks like. You start with a large chunk of input data. This could be terabytes or petabytes of data. This data is then split up into smaller chunks, and these chunks are distributed across multiple machines in your cluster. Then these machines execute what is called a map operation on the local data that's sitting on the disks. And the output of these map operations is then sent to reduce operations, which combines a lot of this data and then produce the final output. So the main stages of MapReduce are the pushing of the data to the mappers, the map phase, and then the reduce phase. And we'll talk about each of these a little bit more. So first of all, let's look at what the MapReduce programming model looks like. So in this model, data is represented as key value pairs. So all the data have a key associated with them, and then they have some values. The keys can be strings or numbers or other kinds of hash values. The values can be basically anything. They can be strings, they can be some sort of structured data, or they can be large amounts of free text, etc. So the values are pretty much anything that you want to have. So what the map function does is, it takes the input key value pairs that are provided as part of the input data and converts them into some sort of intermediate key value pairs. So it maps this input to some sort of intermediate data. So each map function basically starts with the input key and corresponding value, and it generates a list of intermediate keys and corresponding. Now the reduce function typically merges the data that is generated by the mappers. So a reduce function takes, for each intermediate key, it takes all the values that have been generated for that particular key, and then it combines them somehow to generate a set of output keys and corresponding output values. So here's a very simple example. Suppose you have a large number of text files and you wanted to do word count on them. So you wanted to count how many times each word is appearing. So here's how you may implement your mapper and reducer functions. So the mapper is taking two parameters or two arguments. The first is the input key, which is the file name, and the value is the text inside that file. Now what the mapper is doing here is, it's simply tokenizing the whole text. It's splitting up the text into individual words, and for each word it's simply generating a count, which in this case is going to be 1. Now it sends this intermediate data to the reducer. Each reducer now takes, for each word, it takes the list of counts that have been generated by the mappers. And all it does is, it simply adds up these counts for each word. And then it will finally emit for each word how many times it has appeared in the whole input text. Here's an illustration of this word count example. So suppose we have input which basically consists of these 3 lines. The quick brown fox, the fox ate the mouse, how now brown cow. And we have 3 different machines running map. So we sent each line to one of these map functions. The map function basically simply counts how many times each word is appearing in the text. Okay. And then each map function sends each of these intermediate key value pairs, which means each word along with its count to one of the users. In particular, what we see is that the intermediate data, which is colored in red, is sent to the orange reducer. So this corresponds to the words the brown fox and how and now. And the green text is sent to the green reducer. So both of the reducers are getting a separate set of the key space, intermediate key space. And and the reducer simply count up the words and generate the output. So now let's look at the workflow itself as to how data moves along the different machines and how the computation occurs. So in this case, the input data is first of all split up into smaller chunks. Each of them is sent to the machines which would be executing the map. And then the mappers send their output to the reducers, which finally generates the final output. So you can think of the computation as happening in multiple stages. The first stage corresponds to simply pushing the data from your input source to these different machines that are part of your cluster. Okay. So this is where the data is being divided into smaller chunks, and each of these chunks is sent to the different compute nodes. In systems like Hadoop, this is done using a distributed file system, such as Hadoop system or HDFS, where this data is chunked before you start the computation, and it's based on all the compute nodes beforehand. Now, once you have got the data placed on these machines, then you start executing map function. Okay. So what the map does is basically it executes a map function on the data that's sitting on the local disk. Okay. So suppose you started with a large amount of data and you divided it into say 100 chunks, you will have 100 map tasks that are running in parallel, depending on how many machines you have, and they'll be executing on the local chunk of data that they have sitting here. So there is strong preference to run the mapper on the data that is sitting locally. Although there are techniques or mechanisms inbuilt which also allow you to pull data from other machines so that you can do better load balancing and get better fault tolerance, etc. Once the mappers are finished executing, they store the output data or the intermediate data of the overall computation to their local disks. So as far as the mappers are concerned, once they compute the map function, they simply dump the data on the local disk and then they are done. After this data is sent to the reducers, and the reducers then start merging and combining this data to generate the final output. So how do you move data from the mappers to the reducers? So the goal here is to divide the intermediate data across the reducers in such a way that each key is sent to a single reducer. Because recall that the role of the reducer is to take all the values that were generated for each key and combine all of them. So all the data corresponding to the same keys have to be sent to the same reducer. So to do this, you have to do some sort of partitioning on the intermediate data. Okay. And a very simple way to do it is, say, if you have k reducers that you want to run in your system, use some sort of a partitioning function or a hash function that divides the intermediate keys into k reasonably equal partitions. As a very simple example, if you have 3 reducers and your keys range from 1 to 6, you might partition the key space into keys 1 and 2, which go to the first reducer, 3 and 4, which go to the second reducer, and so on. So this operation of sending the data from the mappers to the reducers is what is called the shuffle stage. Okay. So the mappers dump the data to the local disk, but after that, the system basically will start shuffling the data to the reducers, and as part of that, what it does is, it applies this partitioning function. For each key value pair, it figures out which reducer it needs to send that data to, and sends the data to that reducer. So in essence, this boils down to an all-to-all communication between all the mapper machines to all the reducer machines, because the mapper can generate any set of intermediates. So part of the keys have to be sent to one reducer, part of the keys have to be sent to another reducer, and so on. So if we go back to the diagram, that's what the diagram kind of is depicting. From the mappers to the reducer, you have almost all-to-all communication. Okay. In addition, MapReduce also supports something called a combine operation, which allows you to combine some of the intermediate keys at the mapper itself, so that you can reduce the amount of data you have to send to the reviewers. Okay, so this can help you reduce the network cost.